Hi, my name is Julia Silge, and I'm a data scientist and software engineer at Posit, formerly RStudio. Today in this screencast, we're going to use this week's Tidy Tuesday dataset on tornadoes, and we're going to predict how extreme the tornadoes are, how powerful, what's called the magnitude of a tornado. I grew up in Texas, North Texas, just in like Tornado Alley. So this data set has a lot of resonance for the extreme weather, natural disasters of my youth. But also, I think this is a great data set where we can really think about the modeling process, how we set it up, and how how we have many options, and how the decisions that we make really impact the results that we get later on down the line. So let's get started.
Okay, let us dig into these tornadoes. So this is, like I said, this week's Tidy Tuesday data set. I'll just pipe it to view and take a look here. So there are quite a lot of rows of data, lots of tornadoes in this data set going from, 1950 all the way up to now. And we have data on them like when the tornado occurred, the state where it occurred. We also have, latitude and longitude for the start and the end. We have some information like how many people were injured and how many fatalities there were. We have information about the length and the width. And what I would like to talk about is how to build a model to predict this magnitude. So the magnitude is a measure of how extreme the tornado is. So let us take a look at it. So I'm going to just make a histogram of what the magnitude, how it's distributed. I'll do geom bar, so a bar chart actually, like so. So we will have this pop up, and we'll see that lots of mild tornadoes and very few big ones, right? So we've got this kind of relationship that shows up in all kinds of places, including nature. Notice that it is this is a like a label. It's more like a categorical variable maybe than in some ways. Like a tornado can be given a magnitude of 1 or 2, but not 1.5. So it is not really a continuous variable here. One of the variables that's in there, it's called FC, is whether this magnitude is estimated or not. Let's say position equals dodge, like that. And so most of the tornadoes have a real measurement for magnitude, not an estimated one. We could take those out if we are interested in this. Also, I'm kind of interested what this will look like if I look at a log on a log scale, like here. And we can change this position dodge. See how the bar for the 5 is twice as wide because there are no estimated ones, only measured ones. We can change that with that preserve equals single, like that. So often that is what I would more prefer it to look like typically. Remember this, so this is now a count. The counts are on a log scale here, but notice it's still even, like it decreases still obviously, but we see that more detail here when we put this in the log scale. So let's talk about this. It's not really a numeric variable. So how would I go about building a model to predict this as an outcome? I could treat this like a classification problem. Say build a model that can predict what category the magnitude is in. Is it 0 or 1 or 2? The problem with this is that these classes are not really like red, green, blue, where it's more like a small, medium, large, where this has an order to it. And using this as a classification model, we will not, we'll lose that information that we have about how these are related to each other. Like, and so a tornado that is truly a class 5, it getting predicted as a class 4 is very different than it being predicted from a class 1 in terms of how wrong it is. And classification metrics don't take advantage of that. So I think that's out. That's not a great option. Another option we have would be we could treat it as a ordered outcome. Like and what this function does in the mass package is it fits models to an ordered factor response. And that is about perfect, actually. Like, that's the exact outcome that we have. The thing is, though, this data that we have is quite big. It's quite big. We you know 60 some odd thousand tornadoes that we have in this data set. And in those cases, so this is a linear model, and almost certainly the tornado data has in it complex interactions that that a linear model will not capture, whereas a more powerful model like spoiler alert XGBoost, would be able to do. So this is exactly the right kind of thing, but this is a linear model. So I feel like that's probably not going to be the best option. Another option I could try is if we look at this plot and we see, we could treat this like counts, and it's like the data generating process here is generating counts. And maybe, if you look at without the log scale, maybe it's actually counts that have extra zeros somewhat. I don't know, maybe not. Either way, we could treat it like we could treat it as if it's counts, either with extra zeros or not, and use a Poisson model. Again, these are linear models. I am not aware of any implementation of these kinds of modeling these kind of outcomes that are not linear. Like, the main ones that people use are all linear models. And so again, it's not going to be a great fit. So what should I do? How should I try to build a model to predict this? Well, what if I go back to that first thing I said where I'm like, this is not continuous? And what if I just treat it like it is? What if I just treat it like it is a regression problem? That's the example I'm going to walk through, and we're going to see what it does and does not do well, so that you can understand when you have data like outcomes that are not a perfect fit for the different kinds of models and how they are formulated, what is it that we go ahead and can do? So let us take a look at tornadoes here. And, we've got lots of different variables. Let's do a little more EDA so that we can talk about, have a little more knowledge as we go into building our model. So first, let's look at this, this state variable. And let's just calculate the mean. Remember that there were NA values in there. We saw those pop up in the plot. And I always, if I'm summarizing, I always kind of like to look at the N, how many are there. So you can see here, very few tornadoes in Alaska, and they are very mild. Very big contrast to, say, Arkansas, which has a lot of tornadoes, and also they're more extreme. So this state, if we were to look at, state, it's like a measure of location, right? We can see here that we have quite dramatic differences in how extreme tornadoes are in these different states. So I think I'd like to use that as a predictor. It does have 53 levels, like 53 values, which is getting to be pretty high cardinality. So I'm gonna take an approach. If I have two main sort of options here. One is I make dummy or indicator variables with the state, and that means I'd have about 50 new columns, which, I might not want to do that. That doesn't sound like a great option. Or I can use a likelihood encoding or effect encoding as part of my feature engineering. So we'll talk about how to do that. Next, let me look at one of these features or predictors that I know are of course going to have a strong relationship, right? Strong tornadoes cause more injuries and fatalities, certainly, right? So let's look at how that plays out. Whoops. Let me. I'm going to change the magnitude to a factor, and then I am going to put that on the x-axis. I can put the injuries on the y-axis, and I'll just make it have a color so we can see it a little more clearly. And let's make this a little bit transparent, like so. Okay. So on the x-axis is the magnitude of the tornadoes, and the y-axis is how many injuries. Let's get rid of those NA values. I'm going to have to clearly get rid of those when I build a model too, because you can't have a NA value in your outcome. Okay, so here we see big shifts, right? This is probably on a log scale as well. We'll be able to see more if we put it on a log scale. So for the most extreme tornadoes, many more injuries than the mild ones. So if I wanted to visualize this a little bit easier, I could do this. If I do this, notice what happens. You can't take the log of 0, so it is removing all the zeros, which is actually a terrible thing for me to do. Very bad. I should not do this, because 0 injuries is meaningful, and we want to keep that when we look at it. One way, sort of cheater way to get across this is to add 1 to that value. So this is a pretty good option. This is not the worst option. I will admit I have done this a lot of times, but it might even be better. It might be more like a more easy to interpret plot if I use something. It's in the scales package, and it's like a pseudo log trans. So if you see what it says there in the documentation, it transitions to a linear scale around 0. So this lets us do that. This one, I think you can, like maybe we want to say, like, do it on a 10. It's not a huge difference, but anyway. So this is probably a better way to visualize it. So notice that lots and lots of the low magnitude tornadoes have no injuries, although we do have outliers here, but then it really dramatically scoops up. So by the time you're at tornado magnitude 4 or 5, these things are enormous and strong, causing lots of injuries. We could change this to fatalities right here, and it would just be similar, but there are even fewer of them. Like, fewer people die than are injured, which makes sense. Okay, so let's call that good for our EDA, and let's start building a model. So the first thing we're going to do is we're going to spend our data budget. So I'm going to take this same thing I have here. I am going to pass it to initial split. I'm going to stratify by magnitude, which so stratification, when you're doing resampling, almost never hurts you, and sometimes it really helps you. I suspect this is a situation when it would help you, because the magnitude is distributed, as we saw in our plots, right? It's distributed. Can it keep going backwards? Like this, where there's lots and lots of 0 magnitude tornadoes and very few high ones. So if we want to be able to predict those really high ones, we need to make sure they're in our testing sets, and evenly split up. So let's call this tornado split, like this. Definitely need to set a seed here. And then let us create a training set. Let's create a tornado test, a testing set, like so. And then let's create some cross-validation resamples. I'm just going to have the seed again here, just in case I run these out of order. or not out of order, but if I rerun them in a not totally top-down way, I get the same results. I'm going to call it tornado folds, and I'm going to say vfold cv tornado train, and I'm going to stratify this as well, mag, like this. So what do those look like? There we go. Okay, so here we have our 10 cross-validation folds. So this all together is the training set. Notice I'm making my resamples from the training set. This is a training set. And then I have 10 resamples where this is like a little mini training set. We call it the analysis set. This is a little mini testing set called the assessment set. So as I go through and I do, feature engineering and tuning of model parameter, hyperparameters, these are the 10 data sets I'll use to be able to say what is the best choice. Okay, that's the first step of my model building process, spending my data budget. The next part of my model process is feature engineering. So I'm going to use a recipe here. And if you look back at what the variables are that I have here, I'm going to predict the magnitude. Let's say the date. Like I said in the intro, I grew up in Tornado Alley, like a part of the country with a lot of tornadoes. So I know certain times of year are tornado times and other times are much less so. Also, this will let us use the year. Let's put in that state, which remember we're going to want to handle with some feature engineering so that we don't end up with 50 new variables. Let's say the number of people that are injured, the number of fatalities, length and width, which are the size of the tornado. And yeah, let's call that good. So I will pass in a little bit of data here. Oh, it's a lot, but I'll pass in some data here to tornado recipe. I will pass in this data here so that the feature engineering recipe can learn what it needs to do. And now let's start with what steps I need to take. So first, I am going to, first let's deal with the state variable. So I'm going to load the embed package like this, and I am going to then use a function from the embed package called step likelihood encoding. I could do it with regular old GLM, or I could do it with these like fancier methods. In the interest of time, let's do it with GLM. So I am going to the variable that I want to encode using a likelihood or effect encoding is the state. And then this is a supervised process, so I have to send in the outcome. So what is happening here is that we're going to make a little mini model as part of our feature engineering that maps the states to an effect on the outcome. So what we can do is instead of having Texas, Arkansas, Alaska, we will have numbers that are from this little mini model that say how much of an effect on the outcome does this have, only looking at those two variables. So this is a supervised feature engineering approach. So it's really important that we use very healthy resampling to make sure that we are getting a more accurate estimate of how our model will perform. Okay, so I've done this. Now let's handle that date. It is called date, if you remember from up here, date. And what I'm going to do is I am going to set some features. I want to use the month and the year here. I would not expect the day of the week to make a difference. It might be interesting, but to see if it does. And then I want to get rid of the original date column here. So we want to get rid of that there. And so the outcome of this will be a categorical variable. It will have, the months of the year in it. So I am going to use step dummy for anything that's left over. I think it's just the month, but we can just use that there. So now anything that is still categorical, it will change into a Dummy or indicator variables. Okay, so let's look at how this turned out. So I don't need to do anything with this recipe to use it for tuning or training, but for debugging, it can be useful to know how to handle recipes so you can see what is going on. So if I say bake new data, new data equals null, like that. And then let me just put a glimpse here so we can see what it is. So what it's doing is it is prepping the recipe, meaning learning from the training data what transformations need to be performed. Remember that includes this little mini model. And then it's baking the new data, which means baking with new data equals null, which means pulling out the training data. And then hopefully it will print out here. Okay, that took a little sec. It's pretty big data and it had to learn a little model. Notice what's in state now. Instead of things like Alaska, Texas, Arkansas, now there are these numbers. And so these are the numbers that have been learned from the training data to be able to map from this state to this effect on the outcome there. And then also notice we've got our months of the year, and this is all zeros and ones. So it's 0 if it is not that month, and 1 if it is that month. So this is what dummy variables or indicator variables look like. Notice there's no January. If I would have changed this to 1 hot equals true, I could have had January there, especially if you're dealing with a linear model. You do not want that base level because then it can't do its matrix stuff very well. But for a tree-based model, we could put it in case some people say we should, but it's fine. Let's just keep going as is. Okay, so that's feature engineering. So first step, data spending. Spend our data budget. Second step, feature engineering. And now let's get to a model. So I'm going to make an xgboost model specification. I'm using xgboost for just the reason that I said when I was talking about how are we going to model this. This is pretty big data with things that I know are correlated with each other. I know injuries and fatalities are correlated with each other. I know length and width are correlated with each other. And it's a big data set. So when I see that kind of situation, I think, xgboost is going to be my friend. xgboost has a lot of hyperparameters, so we have to tune them because there's no way to know ahead of time what the right value for these are. We have to use our data to find it out. I am going to set the learn rate kind of high. So this doesn't take 1 zillion years to get to something. So let me set the engine to xgboost, and then let me set the mode. So notice here, I am setting this as a regression model. This is the choice that lets me use, xgboost, and it's as this implementation of xgboost. Remember, this is the kind of weird thing that I'm doing given how this outcome is. So we're going to see how this turns out given that. So let's say xgboost workflow, and let's put these two things together. So tornado recipe and the xgboost tunable model spec here. Whoops, I better make it first. Okay, there we go. So this workflow, if I print it out here, it has my pre-processing in it. It has my model in it. This is tunable right now. So we don't know the right answers for those values. We have to learn it from our data. Speaking of which, let's do that. Okay, so I am going to tune this. You know what I'm going to do? I am going to use racing, because the thing about xgboost is that you don't really know what these should be, but often some of them turn out really bad right away. It's like, oh, this one's clearly terrible. So we can use one of these racing methods. So what was happened is we'll use those resamples that we made, and we will try all of the different hyperparameter combinations and see which ones turn out really bad after the first couple of resamples, and then throw those away and not keep going with them. So it can be a really big time saver. We can do either one of these. I tend to default to tune race ANOVA often. So it uses an ANOVA model to see, is this one different? Is this set of hyperparameter configurations worse than the other ones? Can I throw it out? Okay, so I pass in the workflow, the tunable workflow. I'm gonna pass in my folds. This is the data it's going to use for tuning. I am going to maybe bump up the grid a little bit. I think the default is 10, but there's so many, there's so many different possible values or possible hyperparameters here that I'm going to bump that up a smidge. And then I am going to, I'm going to say use the racing control. Oh, I never loaded that. Okay, let's do the race control, and I am going to here let me do this so you can just see it as it goes by what is happening there. Okay, I sure had better save this as something. Don't need to do it all and not assign it. And then I'm going to set seed here too, just so that this is reproduced. So this part includes randomness. So let me kick that off. This is for sure a long part of the process. So I'm just going to talk through what it's doing and then I'll pause the video. So what's happening here is that I am taking my 10 resamples like these, and I'm trying, I picked one, it's picking one set of the hyperparameters, and it's trying it with all of the resamples. And I'll do that a little bit, and then I'll start using an ANOVA to decide if any of them are statistically much worse, and it will start throwing those away. And then it'll keep going and going until it ends up with which ones are the best ones. So I'm not going to evaluate all 15 hyperparameters on all 10 resamples. Some of the hyperparameter configuration are going to get thrown away after running this on the first part of these guys. So let's pause this and then we'll come back. Okay, the racing finished, and now we can look at this these messages that we got and see what happened. So, after it did a couple of folds, there were 8 left, and then it kept going, and there were 2, and there were 2, and then by the time we got to the last fold, all but one parameter combination were eliminated. So it finished. We can look at the results like this. So we've got our resamples. This is the order that we went in. So it started with, this one, so forth. We've got metrics that were measured. And just notice this, the first couple that were done have 30 rows because it's the 2 metrics, across all of the resamples, so this is 15 times 2 because our grid was equal to 15, and then it goes down. Notice, and by the end, we only evaluated the last resamples on the one remaining hyperparameter configuration, and that is the one that is the best one that we have down there at the end. So that's how racing methods work, which are really nice. So we can do things like pull out the metrics from these racing results. So this is the overall. Oh no, this is the metrics for this last one. It only does the ones that have 10 in it by default here. So this is that best result. Okay, and let's look at what these numbers are. So R squared around 0.6. Not enormous, right? That's the amount of variation that we explain with these predictors. The RMSE here, that's the root mean squared error, and this is on the same scale as the outcome, which remember is magnitude. So if you went from 0 to 1 to 2 to 3 in the tornado magnitude, this is that, it's on that scale. So it's like 0.5, 0.6 of a magnitude integer. So the root mean squared is like 0.6, and remember that these are like 1, 2, 3, or 4 or 5, like that. Okay, we can also look at get a visualization of how the plot race, like that. Okay, and so this is how the racing went. Notice that when we started over here and then we go across to the right. So at the beginning, we tried all the hyperparameter configurations, and some of them are super bad, and we can throw them away after only a few iterations. And then we keep going, we can throw away more. We only had 2, and then it decided, okay, I can throw away that one as well. I have enough evidence, statistical evidence that this one is better than this one, and then it keeps on going just with the one all the way to the end. So that is our racing, which is excellent. Okay, so now that I have that tuning done, I can take that XGB workflow, and I can finalize it. So I'm going to finalize the workflow like this. And what I'm going to use to finalize the workflow is the best one. So if I select the best from the result that I have, like this, that's going to be these set of parameters right here, 15, lots of trees, min n, like this. And then I can pass this to last fit. And so what I pass to last fit is the split that we have, tornado fit, let's call this. So I'm taking the tunable workflow that I have. I'm updating the parameters so that they're no longer tunable, but instead now they are set to these values here, 15, 18, 77, 37. And then I'm using last fit, which is it fits one time to the whole training data and evaluates one time on the testing data. So what this is the first time that I've used the testing data. Remember that all through this other process, when we were tuning, that was using the resamples, which are like little simulated versions of the data set that we can use for tuning. Okay, and we can look at what that likes. It returns a tibble that has this is the training and testing data, metrics. We can get out predictions. If I were to get out the metrics on this tornado fit like this, what this does, this is now the metrics measured from the testing data, and it's about what we expected before, which is good. It confirms we do not have a lot of overfitting. And we can also get out these predictions, which I am interested in this because this would be one of the things that I would look at to see, was this actually a terrible idea, what I did, to treat this as a regression problem? So what happens if I make a histogram of the predicted values here? So I'll do geom histogram like so. So, okay, so this is not on the log scale, but look at this distribution of predictions. This is actually not so bad. So notice there's not a lot of values below 0. And the range here is actually just right. Like we don't end up predicting tornadoes that are 10 or 20, that have a magnitude of 10 or 20. And this distribution is also not too bad. Not too bad, we could, let's see, I can do like a quick, let's just change this. So mutate mag equals factor mag like this. And then I will put the real, so this is the real value, pred fill equals mag like this. And then let's, we can do like what I like to do here to make this easier to see. Okay, collect predictions, pred, mag, pred, what happened here? Collect predictions, tornado fit, mag, factor, mag. Oh, not a histogram, a box plot. There we go. Okay. Okay, and so this is for things that have a real magnitude of 0, 1, 2, 3, 4. What's the distribution of predictions? So we can see that this looks pretty good. Like the median for 5, well, is a little low, so we're under predicting the high ones. and we've over predicted the low one. So we have some, this is not perfect. This is not perfect, but this is actually not so bad. And the thing that we would do maybe to compare would be to use something like the Poisson or the ordered outcome variable, and we go back, do the same thing, and see if, like, does this distribution look better? It might not. The things like that can have a hard time predicting things that we don't have a lot of, and or the zeros. And then we would also compare it to the metrics. How good of a job did we do predicting? So we could go back and try it with a different approach and see how these two things turned out. How did the metrics turn out? And then how did the distribution of predictions turn out? So yeah, not so bad, not so bad. Let's do a quick variable importance, because that is always a good idea with xgboost. So here what I'll do is I will extract the workflow from this fitted, this object that has a bunch of fitted stuff in it, and then I will say I need to take out the parsnip fit on the inside to work with VIP, I believe, and then I'll just call VIP num features 10. So the top 10 features here. Whoop, yep, gotta load it. So this is telling me variable importance for my xgboost. So most important, injuries. Next, length. So how big is it? Length and width are both here. Year is here, which, you know, there is a change with year because of climate change, like more extreme tornadoes as time goes on. Also notice state is in here. It's in the top 1, 2, 3, 4, 5. So it's in the top 5 most important predictors. So what that tells me is that it was worth it to do that feature engineering that we did. Months are also in here, like the high, you know, April, May, June, tornado time of year. Okay, as a last little thing here, it's good asking when are you done with your model, and if the goal is for you to deploy your model, then we're not done here, but instead we need to be able to move towards deploying it. So I can create a vetiver model here, and I'm passing in the fitted workflow, and then I'd give it some sort of name, like I could call it tornado xgboost, like this. Let's just call that V here. And so this would be an object that we could then use and deploy to some place where we want to serve predictions, like, you know, Posit Connect or a Docker container or wherever it is that you need to serve your predictions from.
All right, we did it. We took this data set on tornadoes and talked about what would be the options and the way we could formulate this as a modeling or machine learning problem. If you were going to use this data set and try something else, it might be interesting to see what kind of different results do you get if you try an ordered outcome kind of model, or if you try maybe using something like Poisson regression. I'd love to hear about how that goes if you try it out. I also think it's this interesting data set because of how we used feature engineering together with model estimation, then combine them and then use that to estimate what kind of performance we would expect to see on new data. So I hope this was helpful, and I'll see you next time.